Okay. Well, thank you for attending. I will talk about, if you remember, during my talk on Tuesday, I presented a result that I was calling the Emergent Second Law, and I will explain you the derivation of that result. Okay? So first I will sketch a plan for the lecture, which is the following. So first I will start discussing Markov-Champ processes with a macro limit. And in this context, the main dynamical object we will care about will be the probability to be in a given state of my system. I will specify all this later at a given time. Then we will derive from the fact that a macroscopic limit exists, we will derive a dynamical large deviations principle, which will tell us that this object, the probability to be in a given state and at a given time, satisfies the following limit. So in the limit of large omega, where omega is my scale parameter, can be asymptotically written as e to the minus omega, some object that is called the rate function. And here, instead of m, I will use an x. I will explain the relationship between the two in detail later. But the important message now is that instead of tracking the evolution of the probability distribution, we will track the evolution of this rate function. Okay? And from the dynamics of the rate function, we will obtain two properties. First, we will see how, from the dynamics of the rate function, there is a deterministic dynamics emerging. So we will see how from the stochastic, because of having a macroscopic limit, how from the stochastic dynamics we have an emergent deterministic dynamics. And also, we will write down the conditions that the steady state rate function must satisfy. Okay? And then I will write down the main result I talked during my talk. I explained during my talk on Tuesday as a combination between these two things. So the emergent second law I mentioned the other day can be understood as a result that combines these two objects. Okay? Yes, please.
So when you say deterministic dynamic emerging from the stochastic dynamics, what comes to my mind is the Ito-Langevin process.
Yes.
And then you have the diffusion equation. For
yes, exactly.
Is it the same thing, or is
it is not the same. I can explain you why. Okay, this is a complicated story, but you can think in that context, the macroscopic limit that I'm going to take in the context of Markov-Champ process, and actually the Emergent Second Law can be derived for diffusion process if you take the weak noise limit, which is considering that your diffusion tensor in the Langevin dynamics scales as 1 over your scale parameter. Okay? Yes. Okay, so let me start. This is just a sketch of the relation, so let's start with this. I will start here. Okay, so first I am going to assume that I have a system for which the states the possible states of the systems can be labeled by a vector that lives in a space which is a set of natural numbers to some dimension. Okay? So for example, n can be n1, n2, nd. Examples, chemical reaction networks. I have a vessel with different chemical species reacting between themselves. So N1 is the number of molecules of species 1, and 2 number of molecules of species 2, and so on. Another example, electronic circuits. I can think about it as a set of conductors. So N1 can be the number of elementary charges in conductor 1, the number of elementary charges in conductor 2, and so on. Okay? So let's consider, for example, the case D equal 2. So my state space is a grid. Of course, this extends in all directions. Okay? And I can have sham process. I can have a sham process in this state space. For example, I can have a process that takes me from this state to this one, or from this state to this one, or whatever other state. Okay? So what? The end each point is one of my possible states. Okay? And of course, at a given time, in which state I am is a stochastic variable. Okay? Cool. So each of these processes, I will label them as rho. Okay? So for each, let's go back to white. For each transition, so transitions. So each transition rho can be characterized by the distance between the final and the initial state. So, for example, transition rho will take me from a given state n to a given state n plus delta rho. Okay, where delta is just that vector. Okay, and also this process, this event, can occur with a probability per unit time that I will call lambda rho of n. Okay? This object, this will be important later on. It depends how far we get. But this object could depend independently on time, could have a time-dependent parameter. I am not going to write that. And at some point, I am going to assume that it doesn't depend on time. Okay? And these situations I will distinguish as autonomous dynamics when this is independent of time, or non-autonomous dynamics when it is dependent on time. Okay. Okay, cool. So now, if I assume that the dynamics of this system is Markovian, I can write a master equation, a Markovian master equation. Yes. Yes. Yeah, can you repeat? I didn't hear you correctly. Yeah, please.
Shift all the states with the same vector delta rho?
Well, not necessarily, but because as you see,
that's why I'm asking. So rho depends on n bar.
Rho does not depend on n bar.
So it doesn't take all n bars to the same. So let's say n bar is 1, 0, 0, 0. Let's say d equals 2. So let's say it takes 1, 0 to 1, 1, right? Mm-hmm. Does it take 2, 0 to 2, 1?
It might or might not, and that information, you code it in the dependence on n bar. You see?
Okay, but it will never take 2, 0 to 2, 3.
So let's say that you have this.
It either takes 2, 0 to 2, 1, or it doesn't.
Let's put write down exactly your example. So you're saying, what is the initial one?
Let's say delta rho is 1, 1.
1, 1. Okay, perfect. So you have a transition that takes you from here, let's say, or let's this 0, 0 to 1, 1.
Yeah.
Okay. So you have that process. That process is possible. So what is your question?
it doesn't take all points to one, it doesn't shift all the points.
It might or it might not. That you, the model, that depends on the initial state. So now you are asking me, okay, so if this, so let me reinterpret your question. If this process is possible, is this process possible also? That is your question, right? Perfect. So it depends on what is the value of this function, because this is a probability per unit time. So if, let's say rho is, as you say, 0, 1. So if this is the 3, 1. So if lambda 0, 1, which this is rho, evaluated at 3, 1, if this is different from 0, it means that this process has some probability per unit time to happen. You see? But if this is equal to 0, then this process cannot happen. You see how you encode the information here? No. Lambda is a real function. Lambda is a function from your state space to the positive real numbers. And that is the rate.
From 0 to infinity.
Yes. And that is the probability per unit time. So it has units of 1 over time to have a transition. To have this specific
May I ask a question? Hello?
Go ahead.
May I ask a question?
Yes.
The point is, when you let's go to the graphs that you were making.
Yeah.
If you go from, can you center it? Thank you. The point is, you say that the first arrow, if that is possible, the second also is possible. What I want to know is what about the transition from the first end state to the second first state? I mean, what is no, because I mean, you are telling me that the system, you started saying that the system was in a way deterministic and stochastic at the same time.
No,
so,
I never said that. The system is stochastic. And then by taking an appropriate limit, we will derive a deterministic dynamics.
Okay. All right. Thanks. Okay.
Okay, why don't you keep going and I'll try to figure it out
Yes.
as you go along. Okay, go ahead.
I think this might help. So let's consider that you are modeling a chemical reaction system. So you can have molecules of type A reacting with molecules of type B, giving you molecules of type C. So you have this. These are your variables. And whenever you have an event like this, whenever two molecules of A and B are in the same place and they react with some probability, they produce a molecule of type C. Well, in that case, your delta rho will be -1, -1, 1. Okay? Okay? And in this case, you will have this process will be possible with some rate which will be different for each case for all the possible values of NA and NB different from 0. It's as simple as that.
Okay.
Okay?
Go ahead.
Okay. Okay, so each possible transition that can happen in a system has associated a change vector, delta rho, and a probability per unit time to happen. Okay? Cool. Now, most of the things I am going to talk about are actually general properties of Markov-Sham processes. But I need to impose an important restriction on the class of Markov-Sham processes, which is the one on it is the hypothesis of microscopic reversibility. Okay? Which tells me that if a transition is possible, the reverse transition should also be possible. So, if, let's say, this particular transition has some chance of occurring, is not 0, then the reverse transition, which is this one, should also be possible. Okay? Cool. Okay. This is not detail balance. Detail balance would be putting a condition the ratio between these two. I am not doing that yet. Okay? Well. Exactly. Yeah, yeah. Yeah, yeah, it can be time dependent.
Yeah. So I was asking, what I was asking? Well, first I asked about detail balance, but that's another condition that maybe he will use later. And then I asked the Markovian properties that lambda rho does not have a memory, so maybe it doesn't depend on time?
No, yeah, it can depend on time. Suppose that this, for example, the rate of this specific reaction will depend on temperature, for example, on the temperature of the solution. Suppose the temperature changes in time, externally. That is something that is happening external to the process, you see? It has nothing to do with the history of the process, you see? For example, or an external magnetic field, whatever, okay? Okay, so I will assume that the process is Markovian, so this object, which is the probability to be in state n at the time t, will evolve according to a Markovian master equation, which is very simple to write down. I sum over all the possible process of all the transitions that take me to the state I am looking at, minus the sum over all the transitions that take me out of that state. Okay?
You don't want to say that they're equal? You want to say they just have to be non-zero?
No, no. I'm just saying, if this process can occur, so its probability per unit time is not zero,
yes,
then the other process should also be possible. So its probability per unit time should also be different from zero.
but it can be infinitesimally small.
Yes.
Okay, just can't be zero.
Yes, and we will see why in a while.
Okay.
We will see why in a while. Okay. Cool. Okay, so let me. So we have this evolution. This basic equation is a completely general Markov-Chain process. With this condition, it is kind of restricted. And now I will write the same equation in terms of a fancy named object, which I will call the self-information, which is nothing else than minus the log of this, of the probability. Just that, okay? I will, instead of writing the dynamics of this, I will derive a dynamics for this. And for that, I just simply divide this by the probability itself. So here I get minus okay? Cool. And here I get here I have e to the minus, and here this is the self-information. And this, when I divide by probability, this is 1, so here I can do like this. Okay? Here I am expressing, well, the only thing I am doing is expressing the probability in terms of the rate function. Sorry, not rate function, the self-information. Okay? Minus e to the minus I. Yeah. Can you, sorry.
P is equal to e to the minus I.
Yes.
So ddt of P is equal to ddt of I, or minus ddt of I, times e to the minus I. You already dropped, you already divided?
No, sorry, maybe I was not clear.
No, okay.
I am deriving this.
No, I got it. You added a term, you added to the other side.
Yeah. I am just taking this and dividing by P and F.
Yeah,
Okay.
I got it.
Okay, cool. Well, so this is a weird way to write a master equation, but it's okay. So, okay, now I will write here. So what we will do now is to take a macroscopic limit. So we will assume that there exists a scale parameter. I think I am closer to you here, so. Okay, so now I will take a macro limit. Okay? So first I will assume that there exists some, well, this is a, I'm sorry for my writing, but this is a large omega letter. This is a scale parameter. Okay, which I assume can be defined in my system. I will give examples later. For example, in the example of chemical reactions, this omega is just the volume of my vessel. Okay? And then I will define a density, which is defined just as my state vector over the scale parameter. So in the case of chemical reactions, these are the concentrations of each species, the number of molecules over the volume. Okay? In the case of electronic circuits, it's a little more interesting because, as I said, the state space is given by the charge configuration in my circuit, how many charges I have in each conductor. The scale parameter in that case, for most electronic components, the actual size of the component is related to the typical capacitance of a circuit.
Sorry, I got that equation. One is lambda rho of n, and the other is lambda rho of n minus delta rho. Why did you?
Okay, no, it's okay. So this is okay, right?
Yeah.
So I divide all this equation, I divide it by P of nt.
Fine.
Cool. So this gives me this, that is okay?
Yeah.
So gives me this, that is okay? Cool. And here, no, you're right, you're perfect. I still cannot do that. This will come later, sorry. I jump ahead. Yeah, you are completely right. So this is, thank you for the correction. Okay, now when I take the macro limit, I will be able to do that, yes. Okay, so as I was saying, I assume there is a scale parameter. I define a density like this. This is very natural for the examples I gave. In chemistry, this is the number of molecules. These are the concentrations. In electronics, these are the charges. And because of how things scale in electronics, you can take omega to be the typical capacitance of each node of your circuit. And if these are the charges, then these are the voltages in each node. Okay? Cool. And I will assume, importantly, that this is well defined. If I take the limit for large sizes of lambda rho of, I will write it like this. Okay, lambda rho of x over omega, this is w rho of x. Okay? Here, I want to clarify this. Here I am using a little notation, right? Look, I define lambda rho to be a function of n initially. And now I am writing lambda rho of x. Okay? So I am assuming, of course, they are not. This is stupidly simple, but hard to explain. So my initial function is this. Now I define a prime version of this one, which is evaluated at the density, and it is just lambda rho, the original one, evaluated at the number variable. Okay? Just by context, I will use the same name for the two of them. And if it is evaluated in n or in x, it is clear which one I am talking about. Okay? I continue. Okay. So I will assume this property, which means that the transition rates are extensive, okay? They scale like the size of my system in the large size limit. Is that okay? Cool. Okay. So I will just rewrite the master equation now in terms of the density.
I'm not sure that what it says. I mean, W can be any function, so it could be 0, for example.
Well, if it happens,
Maybe I don't understand what you're saying. You're saying, so if if the x is over the ladders, right? And you're saying if I take the n's to go to infinity, is that what you're saying?
why n going to infinity? No.
So x is just, let's say n is equal some finite number. Let's
Yes.
say 1, 1.
Yeah.
So, so as omega goes to infinity, what are you saying? You're saying lambda 1, 1 is finite? I'm sorry, it was 0, or I can't follow this last equation.
Okay.
You said it's somehow extensive, but I don't understand what you mean by that.
Well, okay, when do you say a function is extensive?
Well, if you double the energy, if you double the size,
You
you
double
double
the size?
the energy.
Yeah, exactly. If you double the size, you get double that quantity.
Yeah.
So if you divide by that quantity, if you divide by the size, that function is intensive. So if you double the size, it doesn't change.
Yeah, but omega is not the size.
Omega is the size. Omega, you don't know what is omega. I just said omega is a scale parameter. If you want, I can give you examples. So I am assuming.
Just tell me how lambda depends, what it means for lambda to depend on omega. Lambda is a function of omega.
Exactly. Lambda is a function of omega. A function such that this limit is well defined. It doesn't blow up. It could be 0, but it could not be infinite, which is the regular textbook definition of an extensive quantity.
I'm sorry, you're dividing by omega, so why would you think that it blows up?
Sorry?
Okay, I guess I don't. I thought lambda was some probability of something.
Lambda is the probability per unit time to have a particular event. That can depend very easily on the size of your system. For example, in a chemical reaction, if I have a vessel of 1 liter, the two molecules, and with the same concentrations of molecules A, B, this reaction will happen a given number of times per second.
Yes.
If I have a vessel of 2 liters, this reaction with the same concentrations of A and B, so that means with the same X, the same reaction will happen the double of times per second. It's just that. Okay. Is that clear?
I guess so, but what it's not clear to me, suppose it was not extensive. Suppose it was just, it didn't grow when you grew the scale.
Suppose?
Suppose lambda was intensive and not extensive. Suppose it did
well,
not
then this limit is 0.
Yeah, is that a problem or not a problem?
No, it's not a problem. It will just not play any role in the deterministic dynamics or in the results I will obtain later.
Okay, go ahead.
But I want to be sure this is clear.
I'm also confused because when you take omega to infinity,
yes,
an n constant, x goes to 0.
Yes.
So
I am going to take, you will see that I am going to take a limit in which x is not constant, because n also becomes extensive.
So n also grows.
Yes, n also grows.
So you have to take the limit of n going to infinity and omega going to infinity.
Yeah, and you will see, you will see that this is all self-consistent, that will happen. A posteriori, we will see that will happen. So you want to go back to the notation?
Well, I'd like you to put a prime if lambda is a function of x bar. So I know what, you define lambda prime. Lambda prime is just lambda of
yeah,
bar.
well, I define it just to obvious the notation, but yeah, okay.
So now I know what lambda of x. X can go to 0, but because omega is infinite, it means that you're supposed to take that. Okay, that's fine. Okay, I understand your definition. Okay, keep going.
And x bar is not 0.
No.
No, of course x bar is 0. N bar is just a number, right?
That's what I thought. He's saying that
No. Well, this is just, I mean, let's say that you have...
N bar, you told us, were integers.
Yes, but...
Integers are finite.
Let's say that the conditions of the dynamics that you have under this limit will make also n bar grows with omega. What will happen with this?
I originally thought n bar could be any integer.
Exactly. So it could
So how can n bar grow? It's just an integer. An integer can't grow. An integer is a discrete
These
object.
things, I mean, I honestly think, I honestly don't get your questions. So let's put a very particular example, okay?
Yeah.
So let's say that you have a vessel, okay, in which you put molecules of X as a certain rate, okay, and you remove them as a certain rate, okay. So and you do that in order to keep the concentration of X in the vessel fixed, okay? So that means that the number of molecules I have over the volume is fixed, okay? Because of the way I am manipulating the system, okay? Cool. And now suppose I do that with a system that has 2 times the volume. Okay? So under these conditions, under these external manipulations, I have a system for which this variable doesn't change with the volume, okay? And also, it is a time-dependent thing, because if suddenly I drop an extra molecules in the system, then it will take some time for the manipulation to correct and to go back to this constant value that you have. So this is a time-dependent thing that can grow or decrease or whatever. And all the thing that I am saying is that I am assuming this to be well-defined in the macroscopic limit. It is as straightforward as that.
Okay, I guess keep going.
These are simple things, okay? I really don't want to spend time on that. Okay. So, except you have all the afternoon. So, okay. So, let's continue. So, I will take the macroscopic limit by expanding in some way this equation in powers of 1 over omega. Okay? Okay. By the way, this is okay. No, don't worry. Okay. So let me do this carefully. So this is the expansion of this in 1 over omega. Okay? I will also expand this. So here, I actually, the first terms, of course, cancels. And I have here and the second term would be, sorry, there is a minus here. And the second term would be something like delta rho transpose the Hessian of I of X Do you agree with this?
So I should still think, let's say we're doing delta rho is -1, -1, 1. Is that a valid assumption, or are you saying delta
Look, let's say
rho?
that you take the universe, and you count the number of stars in the universe, right? And now you consider that the universe is double the size Is the density of the stars constant or not?
I mean, I would assume that the density of stars is constant.
Okay, well, it is all that I am saying. That the density of I am assuming a situation in which the density of stars is independent of the size of the universe. Is that too hard to imagine?
No, that I can follow, but I don't
Okay.
follow the relation with the equations you're writing. So I'm trying to understand what rho is, delta rho is equal to -1. Can we keep with that example, just because I don't know how the stars has to do with this transition. But can we keep this example of A, B, and C, or is there some easy example I can understand? Where so
what is the concrete
A,
question?
B, and C, right?
C.
A, B, and C. And rho was -1, -1, 1.
Yep.
That I was able to follow.
Okay.
Okay. Now, NA, NB, and NC, you can make as large as you want. I think I can still follow.
Okay.
Okay?
Cool. So?
So delta rho over omega. Delta rho is still -1, -1, 1.
Yep, delta rho is still that.
As omega goes to infinity.
That will go to 0.
Okay, good.
Yeah.
Okay, so we're happy with that. And x is also going to be some quantity which also is infinitesimally small? Or?
No, because I am assuming precisely that I am considering a scaling in which the density remains constant, which is the example of the stars I just gave you. It's nothing crazy, okay?
Okay, go ahead. So, okay.
Okay? Cool. So, so n doesn't go to 0, but delta rho over omega goes to 0. Okay? Cool. So here I have this term here. Cool. So now I will continue in this blackboard. Okay. So I am assuming, this hypothesis is important. Here, notice that I wrote lambda rho of x, so these are actually lambda prime, okay? Keep that in mind. So I am assuming that these guys are extensive, because it is what I express in this way, okay? So look what happens. For example, we have this term here that will be an extensive contribution. And in the lower order, the lower order contribution from this will scale this will multiply this exponential. Okay? So I have an extensive contribution to the derivative of I. We agree? That tells me that under this hypothesis, I will grow to be something extensive. Okay? If that is the case, this I over this omega will be intensive, won't scale for large omega. Okay? Good. Given those observations, the lowest order of this dynamical equation reads like this. I am going to divide everything by omega. Okay? And I am going to define this object. Okay? Well, of course, I am also abusing notation here, right? This is the scaling is in the middle of that x. Let's not abuse notation. Here in the definitions, here. Now, in the definitions, now I am not abusing notation. So to be more clear, these are the lambdas and the I that depend on n, okay? But not here. Here, this is already the scale one. If you want, I can put primes here. I'm clear so far? Yeah, maybe I was not super clear here. I'm sorry. Yeah.
I have a stupid question, but so the lower equation is already an expansion in 1 over omega, and you're dividing by 1 over omega. So you're getting a second order.
I am divided by omega.
But you're expanding in 1 over omega, right?
Yes.
So this is like a second order term in the expansion of 1 over omega, because they're dividing by 1 over omega again.
Yeah, what happens is that, as I tried to explain, if I don't divide, the dominant orders are proportional to omega.
Yeah, so my question is, if you divide by omega the first equation, which is exact,
yeah, no problem, we can do that.
expand is the same result.
Yeah. Okay. I just did this just to. Okay. Well, if you just write the lowest order equation of this, sorry, I just defined this object. This is called the rate function. Okay, in large division theory, this is called the rate function. So now we have the dynamics for the rate function that looks like this. Sorry, here there is a plus. Yes.
Just for me to understand, up to this point, this is already known in the literature?
Yeah, so far.
I'm not from this field, so I apologize.
No. That is a good question. This equation was derived. I mean, the first systematic treatment of this was by Kubo. You know Kubo, no?
Yes.
The Green-Kubo relations, the Green-Kubo equations. So, was derived by Kubo in the 70s.
Okay.
The first. But nowadays, you can also derive it from path integral description of the stochastic process. And in that case, it's interesting. This is a Hamilton-Jacobi equation in which this rate function plays the role of the action in that Hamilton-Jacobi equation. Okay? So this is usual stuff, okay? Cool. Now, I will mention, this is a nasty equation, because you know the nonlinearities here are horrible. You have all the powers of the derivatives of I. So you cannot work directly with this, but I will mention two important properties of this, okay? That I will prove, okay? Well, the first property is that, no, sorry, not property, two features. So first, there is a deterministic dynamics. And this is crucial to get. So I will define xt to be the minimum of the rate function at a given time. Okay? So look, the probability distribution was e to the minus omega, the rate function. So the minimum rate function is the most probable value at a given state. Okay? So x of t is simply the most probable value times t. Okay? Well, it is not immediately obvious, but this guy follows a closed and deterministic dynamics. Okay? So this guy satisfies this. A closed and deterministic dynamics with some drift that I call mu. That is expressed in terms of the scale transition rates and the Champ vectors. Okay? This defines a deterministic dynamics in my state space. Is that okay? We can prove it. If you want, I can just do the derivation of that claim from that equation. Yes, let's do the first step. Okay. So you know that xt is the minimum of this. So So it could nullify the gradient of I. Okay? So xt plus delta t will nullify the gradient of this evaluated in t plus delta t. You do that, you expand, and you get a Hessian. If you assume the Hessian is positive definite, then you can claim this. Okay?
5 longest roads in the world. It takes several years to travel the last one, number 5.
Sorry, I think someone is asking a question, but I cannot hear him.
Traversing all 10 provinces, although it's challenging to cover entirely. You'll discover breathtaking landscapes.
I hear something, right?
In lake country, the snow-capped mountains and wild rivers. Its length is 8,000 kilometers. Number 4, the Trans-Siberian Highway. If you start in St. Petersburg and aim to reach Vladivostok by car,
yeah, no, but I think I can.
One of the most legendary routes in the
Mute audio.
along your journey.
No. Yeah. Okay. Sorry. Sorry for being sloppy with this, but I am used, in the papers I use bold letters for vectors, so I always forget the bar now. Okay? Yeah, sorry. Okay? Well, the second property of that, so I will write this. If the system is autonomous, that means that the transition rates do not depend explicitly on time, okay? They are constant functions of time. Then, under some conditions that we can discuss, there is a steady state. This is an important condition. This might not happen. And okay, this might not happen. We can discuss it if you're interested. When it does not happen, but let's assume it happens. That you have an steady state. Okay. If you have an steady state, it will have an associated rate function that must satisfy this. Okay? Cool. Well, so we have, from the evolution of the rate function, we have two things appearing, or two things that can be defined. There is an emergent deterministic dynamics. There is, in the situations there is a steady state, we know that some constraint on that rate function. Well, from those two things, you can derive two properties that link those two objects, link the deterministic dynamics with the steady state rate function, okay? And I will first show one that was already known and one that is new, which is what we call the Emergent Second Law. It is this nice result I have. Okay? So the first property is the following. And I will first state them, and then I will prove them. Okay? So the deterministic drift evaluated at any point x, the scalar dot product, the gradient of the steady state rate function is always negative. Okay? So the meaning of this is clear. Here you have a material derivative, right? This is the derivative along the deterministic trajectories. So in other ways, if you consider a solution of these dynamics, this property, you can write it like this. Do you agree with that? Okay. So this means, this result tells you that along deterministic trajectories, the steady state rate function always decreases. Okay? On the other hand, the steady state rate function, as any rate function, is always positive. Okay? So you have a thing that always decreases and is also bounded by below. That is a Lyapunov function for a given dynamics, in this case, the deterministic dynamics. Okay? So the first property, the steady state rate function is a Lyapunov function of the deterministic dynamics. Okay? Cool. Yes, please. Yeah, sorry. Okay, let's look like this. So this I, the definition of I is exactly this. So I of xt is the limit as your scale parameter goes to infinite of the minus the log of p of, let's not abuse notation. You remember that p was a p of n, right? So this is omega x t over omega. So you have a probability distribution, you take the log, and the rate function is the extensive part of that log. Okay? This is the definition of rate function in large division theory, usual stuff, okay, in large division theory. Okay? Well. And I didn't mention it, but obtaining the steady state, for systems that are detail balanced, that are at equilibrium, the steady state is just the free energy. And this statement just tells you that, and the rate function would be the free energy density. For equilibrium system, this is trivial. The problem is when you are out of equilibrium, you might reach a steady state that it is not described by the Gibbs distribution, so you don't know anything about the rate function of the steady state. Something that you knew before is that it was a Lyapunov function of the deterministic dynamics. And you only knew that until some time. Okay? Well, now the important part. Second property. The second property is that this same thing plus the scale entropy production rate is always positive. Yeah. Shall we go back to this? Yes. Yeah. Let's do the equilibrium example. So suppose that you have an equilibrium system, right? So if you have an equilibrium system, the probability to observe a given state, okay? Please look at this, okay? Let's focus on this. So the probability to give, so this is an equilibrium situation. So the probability to have a given state is proportional because of the Gibbs distribution, basic statistical physics, e to the minus beta, the free energy of that state. Do you agree with that? Cool. Now, so let's now introduce a scaling parameter. For example, the volume. So the probability of a state, which is some volume times some density, okay, is proportional to e to the minus beta, the free energy of the volumes times that density. Do you agree? Well, what happens if the free energy is extensive? You can take the volume out. And this is perfectly fine. Okay? Well, I should have started that way. I am learning, sorry. Okay. Well, I need to tell you what this guy is.
I'm just trying to figure out what is the picture. So you have a system that's out of equilibrium.
It might be, yes.
But it's relaxing towards equilibrium?
No, it's relaxing towards a steady state.
And the steady state is
That might not be
equilibrium.
in equilibrium,
It's
right?
not Gibbs.
It's not Gibbs. So this is basic distinction between equilibrium state and non-equilibrium steady state. Both are time independent, of course. Both are steady states. But in one, you don't produce any entropy. And in the other one, you do. Okay? So all this is about describing, learning something about something that we don't know much, which is the distribution of steady states in which entropy is produced. When entropy is not produced, then you are at equilibrium and you have the Gibbs distribution.
And
Okay?
Entropy in your case is extensive, because I remember...
Entropy is extensive. And this...
I remember some generalization of statistical mechanics where entropy is not extensive.
No, this has nothing to do with that.
Okay.
That has to do with systems with large range interactions, for example, gravity.
Okay.
This has nothing to do with that.
Different.
Yeah.
Okay.
So the entropy production rate is, this is a scale. So the real entropy production, the real physical, the heat, is omega times time this, okay? So this is the scale entropy production rate. This is a sum over all the transitions of the rate of a transition times the log of the transition rate over the inverse one, the reverse one, the reverse transition. Okay? This is entropy production. It is, well, I can show you. This you can write it as, well, let's discuss later. So for isothermal systems, at the steady state, this is basically heat over temperature, okay? When you have detailed balance, this is 0, exactly, okay? Because, why this is 0? Because this log is a difference of a state function, okay? And so you can, and this is the derivative of a state function as the state is 0, okay? But we didn't assume that, okay? And in that case, then this is you get that is the Gibbs distribution, okay? Okay. So this is a super cool result. Why? Okay, so first it gives you a connection between the steady state fluctuations, arbitrarily far from equilibrium, and the entropy produced along deterministic dynamics. Why? Because if I integrate this equation over solutions of these dynamics, this is a material derivative, right? So when I do the integration in time over a solution, I basically get, I will do the integration. I have ISS in the final point of my trajectory minus ISS in the initial point of the trajectory plus the integral along all the trajectory of sigma plot x tau, okay? And so it allows me to, it doesn't allow me to compute the state function, the steady state rate function in general, but it allows me to bound differences. And that is already good enough. Also, another cool property, I need to define a couple of objects more to claim that. But if you are close to equilibrium, so if these rates are not detailed balance, but are the distance from detailed balance is small, then this inequality becomes an equality. So this inequality is saturated to linear order in the thermodynamic forces. And in this case, you can get, even if that condition is not strictly satisfied, you can get very accurate estimations of this if you are close to equilibrium. And this is crucial by only using the deterministic dynamics. Okay? The other options, if you want to compute the steady state for any of these systems in a normal way, you have mainly two options. First, you run a stochastic Monte Carlo simulations, stochastic dynamic simulations of your dynamics. And then you sample for very long times, and then you reconstruct the steady state fluctuations. Another option is to write the master equation we started with, which is a linear system as a matrix equation, and you compute the eigenvalue, the eigenvector of 0 eigenvalue. That gives you the steady state. For systems that are large, that have, no, it's okay. For systems that are large, for example, you have four chemical species, each of them with an average value of 100 molecules per species. Then you have 10 to the 8 possible states, more or less. So you have to diagonalize a matrix of 10 to the 8 by 10 to the 8. That is prohibitive for moderately complex systems. And this is great because if a system has a macroscopic limit, then you can obtain information about that object, which is very hard to compute, just based on the deterministic dynamics, which are trivial to integrate numerically. Okay? And that is the power of this result. That is what I call during my talk on Tuesday the Emergent Second Law. Why Emergent Second Law? Well, it is emergent because you need, this is a property that emerges in the macroscopic limit, right? Why we call it the second law? Because the following thing. It was this fact, the fact that the steady state rate function is always decreases over the deterministic trajectory, is a Lyapunov function of the deterministic dynamic, was already known. Was derived by a Chinese researcher, which is called Gang, in 1986. Okay. Sorry,
that's something confusing. So this is obviously not invariant under time reversal, right?
No.
Okay. So where did that come in? Where did you stop having? Where did the direction of time?
Just from the beginning. The master equation has a preferred direction.
Which equation?
The master equation? I will write it again.
You can't do that. You can't do that.
Sorry.
Break the board. Just write on the board.
Sorry. dt p of nt equals sum or lambda rho of n minus delta rho. You remember this?
Yes.
Okay, this is a linear system. For a linear, you can write this as dt p equals some generator times p.
So the fact that the lambdas are positive?
Yeah, exactly. The fact, so this is a Markov chain. This is a continuous time Markov chain. Continuous time Markov chain approach monotonously a steady state. So they have time irreversibility built in. Another way to say it, nowhere in my description, if you have a continuous time Markov chain, the state is even under time reversal. Okay, so you don't have degrees of freedom that are odd under time reversal in this description. Okay. Yes. So.
Okay, I must have got confused at some point. You had this reaction A plus B goes to C, right?
Yep.
That's the example that I understood.
Yeah.
But you could also have C goes to A plus B.
Yeah. You remember the hypothesis of microscopic reversibility. So all events can go in both directions.
So that's time reversal invariant. So where did you tell me, where did one direction get preferred in time? I'm missing something, sorry.
Well,
if you can go back, if backwards in time is the same movie as forwards in time, where did I?
Only if you are at equilibrium.
Only, no, let's suppose we're at, I'm just trying to understand why somehow time, something emerged that one direction in time is preferred. I didn't see that. So if the same process can go forward or backward, how do you know which direction time is going? Maybe there's something about Markov that I don't know what the definition is, but if you just have I have a chemical reaction, A plus B goes to C.
Yep.
There's no preferred time direction.
Yeah, there is a time direction, preferred time direction in which entropy increases.
No, that's of course I understand. That's your definition of entropy. I'm asking,
no,
where did that definition come in here? By definition, a state which is less probable goes to a state which is more probable. That's just a tautology. But now you're saying something else. You're saying that somehow in your system, you started with just, maybe I missed something.
But it is, the way this system has a time irreversibility, and the way to see it is that the entropy reduction is positive. So this guy is always positive.
Tautology. You're going backwards.
That is not a tautology. I am telling you, this quantity is positive. That is not a tautology. I have a definition on one side, a 0 on the other side.
No, but you didn't tell me what entropy was. You just said...
Do you want me to tell you what entropy is?
For this case, you didn't tell me what entropy was.
Okay, I can tell you.
Go ahead.
Okay, cool. So,
it must have something to do with I or something like that, but I just don't understand how.
okay, let's write it down. So, I need to introduce the connection of rates to thermodynamics. Okay, so what can I erase? What do you prefer me to erase?
I don't know.
Okay, I will do it here. Wait, let's start filling up the gaps. Sorry, I should have written here. Okay. So we assume that whenever this guy was different from 0, this guy was also different from 0. Okay? Now, I am going to connect these rates to some thermodynamic quantity. So the ratio between them, I can always express them in terms of a difference of a state function that I will call phi, plus something that is not a difference of a state function, okay? Yeah. With the property that, with the following property, this you can show. This, okay, so if you basically, if you change the direction, this thing changes sign. Yeah. Okay. Well, in thermodynamics, when you construct models of thermodynamic systems, this is nothing else but than the free energy, okay? And this is the work that some external sources provide during a transition, okay? Cool. Now, when you, under this hypothesis in which a macroscopic limit exists and everything scales nicely, what is the form that this is called the local little balance condition, what is the form that this takes in the macroscopic limit? E to the minus. Where, importantly, I am assuming, sorry, this I am missing. So here I have big phi, and here I have a small phi. This small phi is the density of this one. So I am assuming that big phi is extensive. And super importantly, I am assuming that the work contributions are intensive, okay? They don't scale with the size. Because they are something that this is energy that is taken up in an elementary step, okay? Yeah. Cool.
But you don't know if W is positive or negative, right?
No, it can have any sign, yes.
Okay.
Yeah. And actually changes sign when you reverse the directions. Right. Yeah. I will erase this, okay. Cool. Yeah. So we can work directly at the stochastic level. But for this, it's not necessary to take the macro limit. We can do it. But let's define then what we, let's give a meaningful definition of entropy production. So, and I will do this at the macro level, at the micro level, then we can take the macro limit. So sigma dot, this is going to be my entropy production rate. I will define it as the change in internal entropy. What is internal entropy? I will write it here. The internal entropy is minus the sum over all states of P and T log P and T, the Shannon entropy.
Okay, yeah.
Associated with my distribution. Cool. And what is the heat? And then what is, so this is the change in internal entropy of my system minus Q dot, I am working, so you see that here I included the temperature directly here, which means that I am working in units in which kBT is 1, okay? So if Q dot is the energy that enters the system, then minus Q is the entropy produced in the environment, okay? Well, you can show, we can do it, this quantity is positive, okay?
That's the point where I got lost.
Sorry?
You can show. That's the point where I got lost.
Okay, let's show it. DTS. DTS is the sum over rho of dt, P and T. You see here that you don't need to derive the log because, so there I wrote the derivative of this times the log, okay? I will write it times the log. Well, good. Then I would have to put a second term here, which is P times the derivative of the log. But that is 0. Because when I derive the log, I have 1 over P. That cancels with this. And then I have the derivative of P, but I am summing over all n. The sum over all n of P of n is always 1.
Okay.
And so the derivative is 0. Okay?
Okay.
Cool.
So there's a minus in front.
Sorry?
There's a minus in front of the first one. It's just minus.
Ah, minus. Yeah, sorry.
Okay.
Thank you.
Okay.
Okay. So, good. Then the heat. So let's write it down, this one a little more. So this, I use the master equation. So this is a sum sorry, this was as over all n. And this is over all transitions of lambda rho n minus delta rho p n minus delta rho t minus lambda rho n p n log p and t. Okay, now I interchange the order of the sum. So I will distribute here this times this, but I am going to use the fact that I am summing over all n. So I will make a change of variable here. Okay?
Minus, right? It's minus delta.
This minus, you mean?
No. You have you shifted n.
Yes,
n
yes, exactly.
So, but then the
But I
log
shifted in the first term.
Yeah, but the term in the log should be with a minus delta rho.
And that is why it is dividing here. I have the difference of logs, right?
No, I'm happy with the log. I'm just think it should be in the numerator should be n minus delta rho.
No, here you mean this?
Yeah.
No, this is plus because I have a minus here, but I am changing the variable. So you see, this is only delta rho plus what is there.
I understand, but the first one is look. You switched n plus delta rho to be n, which means you have to switch n to n minus delta rho, not n plus delta rho.
You say it perfectly, but here you have n minus delta rho. Here you have to switch.
It says oh, sorry, I didn't.
Yeah,
see
this is sorry,
okay.
yeah, sorry. Okay, yeah, this is a minus.
Okay, sorry, I didn't see it. Okay,
Yeah, sorry.
Now it's fine. Yeah, okay, good.
Okay. Good. Good. Continue. Okay. So the heat. Let's go back to the thermodynamic interpretation.
Sorry, are you still showing me why that's positive, or?
No, so far, no. The positive thing is the sum of this.
Okay, so you need the both. Okay,
I need both. This is not, okay.
Okay, go ahead. Yeah.
Do you want to go for it, or, okay?
No, I want to see this.
Perfect.
Curious.
Here, okay. So let's go to the thermodynamic interpretation. So if we are going to interpret this as the free energy, okay, and this as the work provided, so this is the energy that was taken up by the system during a transition, okay? And this is energy was provided by the environment, by the sources, the external sources, okay? So let me yes. Okay, wait, I have a confusion at the moment. How was this going? Yeah. So, by conservation of energy, if this difference does not equal this, okay, it means that the difference in energy was provided by the reservoir or was dissipated into the reservoir. Okay, cool. And that difference is precisely this. Okay, so this is how much energy increased, and this is how much the source is provided. Okay, so I am missing a minus. Yeah. Yeah, actually, the way I write this is actually slightly more. I am going to make a change, but the thing is exactly the same. Minus. Now it is more clear. Okay. Because it's how energy I gain in a transition minus how much I receive from the sources. The difference was in the environment, okay? It's something coming from the environment. Cool. Okay. So the heat rate is equal to the rate, the probability to have a given transition, which is just this, the probability to be in a state. This all depends on T, because this is completely general, right? The probability at a given time to be in a given state times the probability to make a transition times that. Okay? Okay. But now, because of the local little balance condition, that I can relate it, I can write it as minus the log minus the log of lambda rho n over lambda minus rho n plus delta rho. I am using the local determinant condition. I am using that the log ratio, or the ratio between transition rates, is related to, okay? Cool. Good. So I have this. Okay? Good. So let's go back to the total entropy production. Minus, sorry, dTs. Okay. Good. So if I sum now, there is something missing here. Ah, yeah, of course. This sum is also over n, right? So now, if I sum this and this, what I get is the following. This is a minus rho, right? Yes. And this, I forgot to put it here, but this is m plus delta rho. It is the same here. Okay. Yeah. Lambda minus rho n plus delta rho p m plus delta rho. And this is explicitly positive. And yeah, it's not evident. Let's do it. So okay. Let's make it like this. Cool. So last step. This is the last step. So I just copy that, and now I will write it in a different way. Okay, and now let me try to remind how to do this. Mm. I'm super tired. This is very stupid, but I am not seeing it at the moment. No, but yeah. No, this is general. This is general for any Markov process. Yeah. Of course, it's appropriate that it's preserved in the macro limit. Let me just remind how to do this. It's very stupid. This is just a change of variable here. Because this, of course, okay, the idea is the following. This is forward process, backward process. If you change this, if you change the direction, then this changes sign. Okay? So basically, I will put the final result, and then we see how we get there. Okay? Because okay. So the final result is this. Or let's do it like this, sorry. Lambda and minus, there. Minus rho. So this forward process, backward process, okay? Now we sort out the details, but just let's make the observation that if this is correct, sorry. Okay. Okay, the observation is that this is explicitly positive. Why is explicitly positive? Suppose here I have something minus something else over the ratio of the same things. Okay? Right? So if, and this difference can have any sign. But let's suppose it is positive. If it is positive, it means that this is larger than this. And therefore, this ratio is larger than 1, and therefore the logarithm is positive. If this is negative, it means that this is smaller than this. Therefore, the ratio is lower than 1, therefore the logarithm is negative. So this is, okay? So Markov-Sham processes have a direction of time pre-established, okay? They are not, okay, okay. Okay, so let's recap. So the important result I derive, I am proud of, is this one, because it allows you to obtain information. It is very satisfying, I think, from a formal point of view, and it's also very useful because it allows you to as a numerical method, it allows you to do cool stuff, that is otherwise very hard. And I didn't prove this. If we can continue and prove these two things, okay? And if you want to do it, I will do it. I mean, okay. But I'm really tired, I must say. No. Yeah.
Do you have any questions for Nahuel? I don't know if she's listening or. No, I think I got a flavor of
okay, cool. I'm glad.
No questions? Any questions? Okay, so thank you.
Thank you. I mean, this I must say this was a hard experience, but a super useful one. It's the first time I need to explain what I did to people that are not from the field, and it was a incredible hard, but I am happy I had this experience. So, yeah. Oh, thank you for coming. Yes.